Now we shall extend our discussion to a few words on systems. So system, what is a system? A system is a particular device that takes in a particular input and gives a particular output, performing some computations on the input. That is basically the idea of a system. Now systems can be linear systems and time invariant systems, non-linear systems and time variant systems. There are so many possibilities. Now what do we mean by a linear system? So let's understand a system in its block representation. So a system is there that is a block. This is a system. Now there is some input to the system, that is a signal which is xt, and the system computes something on the input and gives an output which is the signal yt. Now this system can be a linear system and also it can be a time invariant system based on certain criteria. So this system is a linear system when it takes one input x1t and another input x2t. So it holds the linearity property that if the system takes an input a1 x1t plus a2 x2t, it shall give an output a1 y1t plus a2 y2t, because x1t when is fed to the system, the output is y1t, and x2t has an output y2t. So this particular linear relationship shall be held by the system. In that case, the system is a linear system. And when does a system become a time invariant system? When the input to the signal has a time delay as x t minus t0 or t minus t0, the output will have a similar time delay, that is y t minus t0. In that case, a time delay in the input results into a same reflection in the output, and that means the time delay in the input doesn't have an effect on the system as a whole. So the system is invariant with respect to time. So the system is time invariant. Now if these two criteria are held by the system, then this system is a linear time invariant system, which we call LTI. Linear time invariant systems. In LTI systems, the analysis goes like, what is the response of the system? But first, some unit base or something like that, so that we can understand how to compute an output of an LTI system. So if the input to the system is a Dirac delta function, delta t, and the output of the system is basically ht, we call this output ht as the impulse response of the system. ht is the impulse response of the system, because with an impulse input to the system, the LTI system has an output of ht, which is the impulse response. Now for a system with an impulse response, what is an impulse function? Delta t is a Dirac delta function, which means delta t is equal to 1 when t is equal to 0, and it is equal to 0 else, that is when t is not equal to 0. So that is a Dirac delta function. When there is an impulse input in the system, the output is called the impulse response of the system. This is the base unit. Now knowing this base unit, that is the impulse response of an LTI system, is ht. So any input to the system, that is xt, goes into an LTI system with an impulse response ht. The output of the system yt shall be given by yt is equal to ht convolution xt, or is equal to xt convolution ht. So this is a convolution operation in the time domain. So by definition, we can write it as x t minus tau h tau d tau, integrating from minus infinity to infinity. This convolution operation can be performed on the input of the system. Knowing the impulse response of the system, then we can get the output of the system. Now if we use the convolution property of Fourier transform, we can easily say that the output response of the system, the frequency response basically YF, is equal to the Fourier transform of the output YT is YF is equal to XF times HF, where XF is the Fourier transform of the input XT and HF is the Fourier transform of the impulse response HT. So the Fourier transform of the impulse response is called the frequency response of the system. So HF is the frequency response of the system. Knowing the frequency response of the system, we can easily compute the spectrum of the output when we know the spectrum of the input. So that is an easy calculation. And so this is how impulse response of the system can be utilized. Now what are their systems? Several types of systems, like a filter is a particular type of a system. So a filter does some filtering operation on the frequencies. There are three types of filters. One is a low pass filter that only allows lower frequency candidates. So what is a low pass filter? So an input with a response as XF has a frequency response something like this. This is XF. So this frequency response has some lower frequency cutoff, and after that lower frequency cutoff, it can only pass until those frequencies. So the system that will pass only those frequencies shall have impulse response HF as a rectangular function, something like this. Multiplying these two, we shall get an output with only the lower frequency components. That should be YF. So this is a low pass filter system design. So for the low pass filter system, the impulse response of the system HF shall be a rect function. So this can be a bandwidth of B here and B here. So it's a total bandwidth of 2B. If we allow this, so it should be a rect 2B of F. So if we do an inverse Fourier transform this HF, we get the impulse response of the system, that is HT. So using an inverse Fourier transform, a rect function has an inverse Fourier transform as a sinc function. So it shall be 2B sinc 2 pi bt. So this is the impulse response of the system for a low pass filter. So that is the design of a low pass filter. Now how to design a high pass filter? So the high pass filter on the other hand shall only pass the higher frequencies greater than that bandwidth. So the rectangular function should be rather on these portions and these portions. So specifically those will pass on the higher frequencies and this portion of the frequency will be passed. So this particular filter only allows those higher frequency candidates. In that case, the HF can be thought of as a 1 minus of rect 2B F. So doing an inverse Fourier transform gives us the impulse response HT. One has an inverse Fourier transform of delta T minus 2B sinc 2 pi dt. So this is the impulse response of the high pass filter, and this is how we can design a low pass filter and a high pass filter. And after this we have to see how it appears for a band pass filter. So band pass filter allows a certain band of frequencies. So in that case a certain band will be allowed in a specific range, here to here and here to here. So this certain band is something like from this is B and this is B and this is some F0 here and this is some F0 here. So it shall be some B plus F0 to B minus F naught. So the total bandwidth was 2B. So a band of frequencies from B minus F naught until minus B minus F naught to B plus F naught is passed, and then this case should be the case of a band pass filter. So the impulse response should be some rectangular function specific to those bands of frequencies. So we can define that HF is equal to rect to B, and we are saying here there was F, so instead F minus F naught is a particular frequency specific there, plus rect to B F plus F naught. So we only allow certain band of frequencies, and that's why it's a band pass filter. Doing an inverse Fourier transform of this HT is equal to 2B sinc 2 pi dt times 2B cos 2 pi bt. So this is how systems can be designed to create low pass filters, high pass filters and band pass filters. Now the idea of creating these filters comes in the idea that these filters or these systems are required later on in certain activities. Like in reality, we have to deal with discrete signals. So we have to convert continuous signals into discrete signals. To convert a continuous signal into discrete signal, we use something called a sampling. So there is a sampling theorem. The idea is a sampling theorem. So how do we perform sampling? So we take a continuous time signal xt, and this is any signal something like this. Okay. Then we take an impulse train delta t minus kt. That is an impulse train. That is a summation here. So that means it's some train of impulses. Okay. So train of impulses. And we multiply the signal with this impulse train to obtain a sampled signal, and that gives us, in the signal's definition space, the impulses are settled like this. So that gives us xst. Now this sampled signal xst is equal to this xt times summation delta t minus kt, which is an impulse train, which is equal to summation x of kt delta t minus kt, where k varies from 0 to n minus 1. Okay, so this is the sampling we are doing. Now we can do the sampling at a particular frequency. That is, when we are doing the sampling, we are considering the period of the samples, the impulse train period, as some interval t. That means this impulse train repeats at every interval of t. Now the choice of t, the choice of the time period t specifies certain things. Like if we choose t higher than some component, so we have to understand what is the highest frequency component of xt. So here the t is basically representing some frequency 1 by t, right? So if this 1 by t frequency is greater than the higher frequency component of xt, then this will result in certain overlaps of the sampled signal in the frequency response. So what is the frequency response of this? Is basically this has some sort of a frequency response, like xt suppose has a frequency response of xf, and sampling results into the periodization of the frequency response. So the periodization will create some sort of a curve like this. Now this. Now if this periodization happens, so these are in certain periods. Now what is the period of this particular response? So after how much time this repeats? So after like a period of 1 by t, this periodization keeps repeating. Okay. Now if the sampling is done at a frequency which is greater than the highest frequency component, then they will be far from each other. So the periodization will not result into overlap of these, because when we try, what happens is that this sample signals frequency response is this. So when we are dealing with signals in the computer, they are basically discretized signals. So the frequency response are always periodized. So to retrieve the signal as a whole, as a continuous time signal xt, what we have to do is we have to pass it through a certain band pass filter, where we pass only a certain band of frequencies, and then we reject these higher frequency components. So it's like we are passing this through a low pass filter, and this is a lower frequency component, and we are only allowing this to come. So as a result, we get only a periodic frequency response as this after passing through a low pass filter, and all these copies are cancelled out. So this we get as xf, and then when we do an inverse Fourier transform, we can retrieve the signal xt. So that is how it works in the computer. But actually what happens, if we have sampled at a frequency lesser than the maximum frequency component of xf, so it results into overlap of these copies. So what happens is this overlaps comes like this. So the frequency response of the sampled signal should be overlapping responses. So something like this. So they overlap each other. And if the rate of overlapping is very high, when we pass it through a low pass filter, what happens is we result into some signal like this, and instead of something like this, which was the original case. So this is called the aliasing effect. So this is aliasing. This is aliasing. So we need low pass filters because of this reason. That's why we need LTI systems, we need to design filters and all those things. But use of the low pass filters in this scenario, where the sampling was not done at a correct frequency, resulted into this aliasing effect, and the signal which we retrieve back by doing an inverse Fourier transform after this is not really the signal which was initially in the beginning. So that is a wrong signal that we retrieve back. So the sampling should be done at a particular minimum frequency which shall be greater than the highest frequency component of the input signal, and that comes from the idea of Nyquist theorem. So that is the Nyquist theorem. If I write it down here, okay, Nyquist theorem. This Nyquist theorem says the sampling frequency Fd should be greater than equal to the maximum frequency component of the input signal response. So let's say the input signal response has a maximum frequency component as 2b. So the sampling should be done at a frequency greater than equal to 2b. So 2b should be the minimum sampling frequency. So it is the lower bound. So 2b should be the minimum sampling frequency at which the sampling should be done. Only in that case we will not have overlaps, and if we don't have overlaps we won't have aliasing. So that's the minimum sampling frequency we must care about, and that is the Nyquist theorem.